Okay. So thank you. I would like to thank the organizer first for inviting me and also creating this opportunity to present my work. Uh, so I'll talk about super-diffusion and crossover from diffusive to anomalous transport in a one-dimensional system. So this presentation will be slightly different from the last three presentations. Here I'll talk about many particles than few particles. So I'll mainly talk about results in this recent preprint that I have uploaded in recently on archive, and also I'll mention some of the results from this publication. Okay, so let me start with the very basic setup of transport. So when you attach two reservoirs of different temperature across an extended system, then energy current starts flowing across the system, and a temperature profile gets established across the system. And after some long time, the system reaches a stationary state where the current and the temperature profile is related by this phenomenological law, Fourier's law, which says that the current is proportional to temperature gradient, and the proportionality constant is called the thermal conductivity, which is independent of the size of the system, and it depends on the system material properties and temperature and other properties. And this suggests that if you look at the magnitude of the current, that decays with system size as 1 over L. And this also suggests that if you have temperature difference which is very small, then the temperature profile in the stationary state that gets developed is a straight line, it's linear. And also, if you start from an arbitrary temperature profile, it approaches to this temperature profile following a diffusion equation. However, all these things are not valid. In systems in low dimensional systems, like in one-dimensional systems or two-dimensional systems, which means that the magnitude of the current doesn't decay as 1 over L, but it decays as 1 over L to the power alpha, where alpha is between 0 to 1. And if you define thermal conductivity as you would define in the Fourier's law case, then thermal conductivity diverges because alpha is between 0 to 1. And such divergences have been observed experimentally in transport, energy transport, heat transport through millimeter long nanotubes in 2017. So this behavior is called anomalous behavior, and it's called anomalous transport. So there are other signatures of anomalous transport. So this is another signature. So here you consider a system that is in equilibrium, in thermal equilibrium, but it is not connected to reservoirs of different temperature. So you suppose you have this system and it is in thermal equilibrium, and you create a small localized pulse at some time, heat pulse, and observe how does it evolve. So it will spread. So in diffusive system, systems which exhibit diffusive transfer, you would expect that this pulse will spread diffusively. But systems which are exhibiting anomalous transport, this pulse doesn't spread diffusively; it spreads non-diffusively. I'll talk about that more later. Okay, so there are other signatures. Many other signatures. For example, when the temperature difference is very small, unlike the diffusive transport case, the temperature profile is not linear. Even if it is the smallest, you get a temperature profile which is non-linear, and it has some singularities. Such temperature profiles usually have singularities at the boundaries. That means the derivatives diverge. And then you can also think of this problem where you start with the temperature profile and how does it evolve to the stationary state. That evolution is also not given by the heat diffusion equation. And another signature is that in equilibrium, if you compute the equilibrium current correlation, that decays with time as power law, unlike the exponential decay in diffusive systems. So these are some features of anomalous transport. And the status is that there is no general framework to understand anomalous transport, and that's why it's crucial to study a specific microscopic model system to understand these features. However, using fluctuating hydrodynamics theory, one can actually describe many of these features in wide class of systems, especially with the recent developments that was obtained in the last decade, and that is actually known as nonlinear fluctuating hydrodynamics theory. So let me briefly describe this theory. So in this theory, you consider a lattice system. Let's consider a lattice system with the Hamiltonian in this form, let's say, which is sum over some local energies, and the local energies have some kinetic energy term and interaction term, where Li is the separation between the displacements or the positions of the successive particles. So generically, such system has three conserved quantities: total stretch, total momentum, and total energy. And this suggests three continuity equations corresponding to three locally conserved quantities. And on a coarse grain level, these equations look like this, where you have this del L del T, like del dou del T equal to minus divergence of the current. Now, imagine you consider a situation in which you have a local thermal equilibrium picture that is evolving slowly. And in such a picture, you expect that these currents can be expressed in the dominant order by the fields itself. And that's how you get a hydrodynamic description. Now, imagine further that this local thermal equilibrium picture is slightly deviated from an underlying global equilibrium picture, where all these densities, 1, 2, 3 is L, U, E, can be written as a global equilibrium value plus a deviation from its value. And you can expand the current in powers of these deviations like this. Let us see if we do it till linear order. So at linear order, you get this equation. So at linear order, you get this equation. And this equation describes ballistic propagation in the sense that suppose you start with a small excitation at some point, let's say at origin, then you can, this equation says that this excitation will actually have a ballistic propagation. Will break into three modes. One mode will sit here, and another two modes will move with certain velocities in the opposite direction. However, if you want to have a fluctuating description, then in this theory you add dissipation and the noise term phenomenologically in the form of diffusion and noise term, which obey fluctuation dissipation theorem to ensure thermalization of goods. And in presence of such terms, if you have this, again, the same initial picture where you have an excitation, then in addition to the ballistic propagation, you will have a diffusive spreading of these excitations. And this, yes? Yes, so I'll make some comments in few minutes, but yeah, there are generally no general theory to derive those. Okay. By the way, these are bare. Okay, but here I don't know in which situation you will have a small imaginary, but I'm considering conserved quantities. You can still have. Oh, okay, yeah, okay. I didn't know that. Okay, okay. Okay, so now if you add the nonlinear term from this expansion, then there could be situations in which this diffusive spreading picture may not be stable against this nonlinear term. And you might get a situation in which instead of diffusive spreading, you might get super diffusive spreading, where this exponent is not equal to half. Okay, so this is I just described this formulation very briefly, and the kind of predictions, not all, some of the predictions. So this theory has been very successful in understanding various features, especially the density correlations. It makes precise predictions of the space-time correlations of the densities, and consequently the current correlations, and you can use that through Ginkgo formula to make predictions about the scaling exponent of that alpha that I was talking about of the current in the of the transport. Okay, but before ending this discussion about this nonlinear fluctuating hydrodynamics theory, let me make some remarks. So first remark that I want to make is that this theory provides a fluctuating hydrodynamic description at a mesoscopic scale. So what do I mean by that? So let me explain this through this picture. So, at microscopic scale, you have lattice. You have a length scale, which is lattice constant. These are the particles. But you take a zoom out view of this. So that means you look at a coarse-grained level. So you coarse-grain over a length scale, which is much, much larger than this. And as a result, these particles appear as fluids. And you write down a hydrodynamic equation, but still you have fluctuations and dissipation. So here you write fluctuating hydrodynamic equation and use those equations to make predictions on a much larger length scale, where you get a macroscopic evolution, where you usually get macroscopic hydrodynamics like super-diffusion or Navier-Stokes Fourier equations like this. So this is microscopic, this is mesoscopic, and this is macroscopic scale. Okay. So in many situations on macroscopic scale NFHD theory, nonlinear. Yeah. Whether you have. No, if you include the second order, and if you see that the solution in the previous order is not stable against adding this term, then of course you have to include this term like that. That's how it is. So suppose you neglect this term, you find out the solutions of the correlation functions, and you see whether, and now you add the second order term as a perturbation and see whether that solution was stable or not. And often in some situations it is not stable. So then you have to find out other solutions. And that's how you do. And second order, usually this, adding the second order term often gives you the leading contribution. So okay, so at macroscopic scale, this theory predicts super-diffusive evolution, which has been observed in numerics. So these are the plots that I have taken from a paper by Suman and Abhishek and others. Okay, so second remark that I want to make is that the diffusion and noise terms are added phenomenologically, which Martin was also trying to point out. So question is it possible to derive NFHD equations, and especially the diffusion and the noise terms? And turns out that there are only very few attempts. One attempt is very recent, both the attempts actually. So this is actually work done by Abhishek, Shinichi, Keiji, and Hongo. And they tried to derive this equation on Hamiltonian systems with the short-range interactions on lattice in general, and they use some projection operator method. So they project observables on space of conserved quantities and space of non-conserved quantities, and then make some Markovian approximation and show that the diffusion coefficients, or whatever the diffusion coefficients that appear in the NFHD equations are actually related to the current correlations, not exactly the current correlation, the projected out part of the currents that is projected out from the conserved space. So that part and the correlation of that and integration of that correlation. Yeah. assuming that there is some time-scale separation and you get rid of the acoustic nodes. Or are they irrelevant? I just want to understand. No, no, they are there. They are there. So you have three types of modes: a heat mode and two sound modes. Are there any? Is there any scale separation between them, or you sort of include all of them in all of the opportunities? When you do mode coupling calculation, you make approximations that the effect of this mode, which is moving, and the coupling of this mode to the non-moving mode is very small, or coupling of this mode, which is moving this direction, and this and another mode, which is moving that direction. No, no, it's just that in the same time scale they're moving, but they have already moved so far that their overlap is very small. So you neglect their coupling. So you make certain. Small parameter. No, there are coupling coefficients. Coupling coefficient. No, no, it comes from the Hamiltonian. It comes from the Hamiltonian. So let me go back. So what I said. So these currents that you write here comes from the Hamiltonian, and these coupling coefficients comes from these coefficients. Of course, the time that in which you are looking at these fluctuations are much longer than the microscopic time scales. Okay. Of course. But different modes actually evolve on the same time scale. Yeah, sound mode. Different properties. One of them is ballistic with time. Other is slower than the ballistic. Right? Okay. So in that sense. Okay, in that sense. Okay. Okay, so this is one work, and the another work we did with Asaf, Julia, and David was here. So this is work on ideal gas of hardpoint particles, but they are undergoing three-particle collisions, stochastic three-particle collisions, and there also we have established NFHD equations with explicit expression of the diffusion term and the noise properties. I'll briefly describe this work later in few slides. And the third point that I want to make is that the presence of the diffusion term in the NFHD equation suggests that you should observe a crossover from diffusive to super-diffusive evolution. And question is it possible to observe this in some system? And here I would like to mention that we have already observed that in this work, but in this presentation, I'll talk about another system in which we can see this crossover. Okay, so let me briefly describe this work on three-particle collision model. So you have this system where you have particles, so hardpoint particles, which are moving in one dimension, and they are undergoing collisions, three-particle collisions, is the following: that you choose three consecutive particles, and you mix their moment in such a way, so that means you have the set of momenta, and it goes to another set, in such a way that the total momentum before and after collision remains the same. And this collision occurs stochastically at some rate nu naught, and in between collisions, these particles move ballistically. That's the model. And we also define appropriately the interaction collisions with the reservoirs. I'm not going into the details. So this dynamics actually conserves three quantities, of course, the number, total momentum, and total energy. Now, such conservations, three-particle type collisions terms are also used by Sanken Ma, actually the same model, and he predicted that this systems would have a Fourier behavior, the normal transport, but this system actually exhibits anomalous transport. And also such collisions are considered in other models by Cedric and Stefan Ola, and also in coarsening processes. In a broader sense, like with total momentum conservation and total energy conservation, such constraints are used in condensation problem by Martin and Schutto in a paper. Okay, so for this system, we could, starting from a microscopic description, we could derive this nonlinear hydrodynamic equations along with the diffusion term and the noise term. The diffusion term, we get an explicit expression for the diffusion coefficient in terms of the system parameters, the density, temperature, and the collision rate, and also the noise properties as well as the strength of the noise. And we found that the noise is, of course, wide Gaussian noise field. As yes, three particle three particle collisions. Not system has many particles. Okay, so as I said, this system exhibits anomalous transport. So in a non-equilibrium setting where you put reservoirs at the two ends, current decays as in the leading order as 1 over L to the power 2/3. So alpha is 2/3 between 0 and 1. But since we know the diffusive term explicitly, we know the next correction, which is the diffusion correction, which is order 1 over L. So this is the current system size dependence. And since we know this term, we can actually rearrange and write it in this form by identifying a length scale. So if I take out the normal part, like the Fourier part, then I have a length scale like this. And if I take out the anomalous part, then this term becomes LC by L. So there is a length scale. So let us take this form. So when L is much smaller than LC, that is this length scale, then I would observe that the current in the system scales as 1 over L. That means I would observe a diffusive transport. But when the system size actually becomes larger than this, then this term will start dominating and you will see a crossover in the scaling 1 over L to 1 over L to the power 2/3. And that is the crossover that we have observed in numerical simulations also, as predicted from this theory. Yeah. Uh, no, if it is the dynamics is this. Yeah, no. But of course, if you consider this very slow dynamics on the bus, then probably it might change. But other than that, okay. So, and I should mention that this crossover length scale. So LC is called the crossover length scale because below that you see a diffusive transport, above that you see anomalous transport, and that is you can find an explicit expression in terms of the density, the collision rate, and the temperature. So I would like to demonstrate similar crossover in another model with two conserved quantities. So this is the result that is now available in this preprint. Okay, so these are the aims. First, starting from a microscopic description, I'll demonstrate how one can establish a super-diffusive evolution on a macroscopic scale with a diffusive correction, of course. And with this diffusive correction, I'll describe a crossover from diffusive to anomalous transport. And for your reference, I wanted to remind you about these three scales. Okay, so this is the system. So we have a lattice, and at each lattice site you have a variable eta, which we call volume. And each variable, this eta variable, this is a stochastic variable. This variable is subject to some potential v eta, and in this work I have considered that this potential is harmonic. So the dynamics of this eta variable is given by this. Eta dot is equal to v prime eta I plus 1 minus b prime eta I minus 1. So note that this is asymmetric in space. This dynamics has asymmetry in space. In addition to this deterministic part of the dynamics, you have a stochastic part, which is that you choose any two sites, successive sites, and exchange their volume variables with some rate gamma. And since you are doing exchanging, then you basically these dynamics will conserve two quantities: the total volume and the total energy. That is pretty clear, easy to see. Yes. Sorry. No, this is I plus 1, this is I minus 1. No, see, this is I plus 1, this is I minus 1. Bit asymmetric, no? Yeah, so it will have a velocity in one direction because of this asymmetry. Yeah, you have a velocity in one direction. Huh? Yeah, gradient, one direction gradient. Oh, so it is eta is square. So the gradient will be eta equal, let me write it. Oh. So eta I dot is k naught eta I plus 1 minus I minus 1. Visible? Okay. Okay. So this conserves these two quantity, volume and energy. Now these conservations suggest me to consider this following locally conserved quantities, which is volume and energy, which I represent by these variables, the hat variables, in this notation, and the corresponding continuity equations you can write down, and you can from this microscopic this dynamics you can write down the continuity equations, and they have this explicit form. It's not. Sorry. Thank you. For the time being, I'm considering it on a ring. Let's say. I'll come back to the reservoir case later. So, and the state of the system is represented by the zeta vector, where you have these variables. And this this is a simple calculation, you can find out this expression. So these are noises representing the Poisson processes that are occurring at every bond, which are represented by I. So this is a bond between I and I plus 1. So I'm just writing it by I plus half. Okay. And this is the notation that I will follow. So hat variables are stochastic variables, which are functions of the stochastic state. And the non-hat variables are averages. And both of them I'm writing as deviations from a global equilibrium value, where again, tilde variables are basically deviations. And if you have a hat on the tilde variable, it's basically a stochastic variable, but still representing the deviation from a global equilibrium value. Okay, so these are the continuity equation. And the Fokker-Planck equation, you can easily write down. It will have, the Fokker-Planck operator will have two terms, Liouville term and the exchange term. This is the Liouville part and this is the exchange part. Here, eta I plus 1 represents the configuration after exchanging the eta variables at I and I plus 1. Yeah. Oh, okay. So these are Poisson processes, the exchanges are Poisson processes, right? So I'm representing those processes by some noise. Yeah. Huh? No, so these events, let's say you consider n of t is the number of such exchanges in a bond. N of t follows a Poisson process like this. It's not it's like increases 1, and then after some time, after an time which is drawn from an exponential distribution with rate gamma, then it will change to 2, and then again you draw another like that. So the collisions, these exchanges occur at times drawn from exponential distributions. Okay, so this dynamics is it has been shown that this dynamics is ergodic, has very good ergodicity property. So it actually thermalizes very well. So the system can be described by an equilibrium distribution, equivalently by a canonical distribution, which are characterized by the temperature, some global temperature and the pressure, and which you can find out from the microcanonical constants that you give into the system, the total energy and total volume and total energy, and H naught is the volume per particle, this is energy per particle. In fact, you get these equations of state in the equilibrium. This is the volume, this is the pressure, this is the energy, temperature, and this is pressure. Okay. Now let me set up the problem. The specific problem that I want to address is that consider a local equilibrium state that you create. So this is the global equilibrium value. But suppose you have a situation in which the system is actually locally in equilibrium, locally described by this canonical distribution, with an average profile that is that looks like this. It's not flat, but it's slowly varying over space for both cases, the energy and this thing. And then you observe the evolution and ask how does this profile evolve? That is the question that specific question that I want to address. And to answer this question, since I have a slowly varying local equilibrium picture, I expect that it will evolve and remain as a slowly varying local equilibrium picture and slowly evolving local equilibrium picture, because you start with a slowly varying local equilibrium picture, which are characterized by average values of the conserved fields. So I write down the solution in this form, local equilibrium distribution plus a deviation. And the local equilibrium distribution looks almost similar to the global equilibrium distribution, except that at each site you have a Ti field and a tau I field, the temperature field and the pressure field. And you have these local equations of state. Okay, and the deviation, it's very simple. You put that form into this equation and you get the deviation satisfies this equation. And initial condition, actually, yeah, this should be T naught, okay. So this part we know explicitly. So this part provides an inhomogeneity to this equation, and you can write down a formal solution of this equation, and the formal solution is this form. So actually, yeah, sorry. So I start at t equal to T naught. I think there was a typo in the previous slide, and so I write down the solution in this form. And they multiply PLE and divided by PLE and rewrite the solution in this particular form where you identifies some phi quantity, phi and phi LE. Phi is this and phi LE is this. It will be clear why I am doing that later. So these quantities you can find out explicitly because I know what is the form of phi PLE. So and if you write down, you do this calculation, it will be in this form. So it's the form of that it is actually in the form of gradient of the local temperature, a gradient of the local pressure, and times some currents. Here you have the time derivative of the local temperature and also the pressure and some quantities which are sort of current, though not in the dimension of current, but you can make it easily the dimension of current just by multiplying gamma. Yeah. Temperature depends. No. The global equilibrium state, you can the temperature is defined by an equation similar to this, where all these are same. It's not I independent. So T is E0 minus tau 0 square by 2 k naught. And E0 and tau 0, you can find out. E0 and H0, you can find out from the initial total energy and total volume that you have given. That you can. Okay. Here I would like to mention that once again, just to remind you that these tilde variables are deviations. These are homogeneous values in the global equilibrium, and so that's why the gradients are same. Here, this LE subscript represents that the rate of change of these variables in the local equilibrium. It will become very clear what do I mean by that. Okay, so these are the explicit expressions of the current. If you do this calculation, it's not very important that you put a lot of concentration in these expressions. Okay, so recall that what we want to do. We want to find out the evolution of the average fields, or equivalently the temperature and the pressure fields. That's what we want to find out. Okay, so to answer this question, we ask this question that the solution that I wrote in this form, I want this solution to be valid at all time of the Fokker-Planck equation, and ask what should this quantity, this fields, what equation this field should satisfy by demanding this to be the solution of the Fokker-Planck equation. And I'll get equations for temperature and tau, and using equation of state, I will get equations for volume and the energy field. and that will give me hydrodynamic equation. That's the plan. And to follow this plan, these are my strategy. So you have these continuity equations, and you you take average on the with respect to this distribution P at each time, and you write down the average values of the currents, and you get these equations. And since these averages can be expressed in terms of the T temperature and the pressure fields, you'll get equations for the temperature and the pressure fields. And using local equations of state, you can express them in terms of the local volume and the energy fields. But I will do this in 2 steps. Yes. I'll do this in 2 steps. First, I'll consider that I'll approximate P by local equilibrium. And in this step, you'll see that I will get a local hydrodynamics. Yeah, of course, I forgot to mention that here I will consider only the linear order terms. I'll neglect all non-linear order terms. So I want to get a linearized hydrodynamics and the macroscopic scale. And in the step 1, as I will show, I'll get a linearized hydrodynamics, which is diffusive. But as I said, this model also exhibits anomalous transport. It has been proved microscopically from microscopic calculation that this model also exhibits anomalous transport. So this cannot be the correct linearized hydrodynamics. So in the second step, I'll consider the correction from the local equilibrium, so deviation from the local equilibrium. And these equations get modified, and we will get a non-local but linearized aerodynamics, and that there will be a non-local kernel, and that will give me super-diffusive evolution, as I'll demonstrate. So, so this coefficient is actually a time integral of the space-time. We'll see that it is a sort of transport coefficient. It can be expressed as a time integral of space-time correlation between 2 currents at different locations, I and L. And to compute this correlation, we'll use fluctuating hydrodynamics at mesoscopic scale. So this is the strategy. So let me briefly describe these steps. So the first step is very easy. You just compute these averages currents in this state and express to linear order in deviations, and you'll get these currents. And if you put them into the continuity equation, you get this diffusion equations. And equivalently, you get equations for the pressure and the temperature field using the equations of state. But these are diffusion equations. They will not predict anomalous transport. So next step, we take the contribution from this correction. So basically, we compute the average current in this full this thing. So first part will give the same answer as in the previous slide, these values. But what do this part will give, this part. So this will be expressed in terms of, I mean, if you use the explicit form of PD, you can express in terms of, in this form, which is a integral over some correlation. Recall this is in this form. So now, what is it? Now, we have to use the explicit expressions of phi and phi LE. And I recall that the phi had these expressions, and these are the time derivative in the local equilibrium. Now, these we have obtained in the first step. So the time derivative of these quantities in the local equilibrium to linear order are these. I put them here and simplify it. And if you simplify, you get this simplified expression, which are again in the form of this gradient times some current, gradient times some current. The interesting fact is that these currents are either nonlinear in deviations or gradient at the linear order, they are in gradient form. Any convective part of these currents have gone away because you have subtracted this part from phi. Phi had the convective part in linear order in deviations, but that you have taken out. If it is there, you are in trouble. You will again produce terms which you already got here. You don't want that. So that automatically gets cancelled. That's the interesting thing, that observation that we should make. Okay, so once again, I want to remind you this notation. Okay, so now, so basically, so you have this expression, and you put this expression in this, and find out the explicit calculation. You find that the current So you don't get an extra contribution at the linear order, even if you from this for the volume field. However, you get an extra contribution at the linear order from this with a kernel, and that kernel is expressed in terms of the current integration of the current correlation. Remember, T0 was my initial time. Now, I forgot to mention that initially this averages was in local equilibrium, but since I want contributions of these currents in linear order in deviation, and these are already linear order in deviation, so I do not need the local equilibrium average, and that I replace by global equilibrium. Okay, next, since this is in global equilibrium, I can use time translation, and then I do a variable transformation, I get this equation. And then since I am interested in the evolution on a time scale much larger than the microscopic time scale, I replace this integral by this integral 0 to infinity. I can approximate it by assuming that you had actually started at a long past. Okay, so I have this expression for the kernel, this explicit expression. So I have everything for the currents. And so now if I put them into the continuity equation, I get this equation. This is the modification that I get from the second step. And if you equivalently using equation of state, you can write down equations for the pressure field and the temperature field. Pressure field doesn't change. The temperature field gets this contribution. You get a non-local term even at the linear order. Okay, so very good. Now the question is, what is this quantity? We have to determine explicitly. So this was the time integral of these currents. Now, if you write down, observe this current, the structure of this current in terms of the deviation, it has a linear part and this part. This is exactly same as this part, the nonlinear part. But the linear part with this will not contribute because the global equilibrium is actually Gaussian in the deviations. So that means you have only the nonlinear part correlation. And again, this doesn't actually make sense in the sense that if you take a finite system and perform this integral over 0 to infinity, they will be independent of I and L. To make sense of this, you take this limit first. So you have to take the infinite system size limit first, and then take this limit, and then that's how you have to make sense of this coefficient. You can actually give a very good, more rigorous argument. But if you're interested, we can discuss that later. So basically, we have to compute this quantity, this 4-point correlation. Now, to do that, and also in the infinite n limit, n going to infinity limit, we have to do that. So I consider this effective dynamics for the volume field. Actually, the volume field is actually same as eta. So the eta has this dynamics in terms of these Poisson processes occurring at the bonds. But since we are interested on a dynamics at a larger time scale, so you write down an effective dynamics on a time scale which is larger than the microscopic time scale. And on such a time scale, you can actually replace the Poisson processes by Brownian noises with some strength. So I have an heuristic derivation. I am not going into that, but you can actually derive this equation. And since we are interested in the n going to infinite limit, it is convenient to start with these dynamics on an infinite lattice with these boundary conditions. And the initial conditions are chosen from global equilibrium. So here I would like to make a remark that this is a fluctuating equation. This is actually similar to the fluctuating hydrodynamic equation that you write in the non-equilibrium fluctuating hydrodynamics. In our specific case, we do not have a nonlinear term for this field, and we require only this field. But in general, you will have a nonlinear term also. Okay. So what is the solution of this equation? So this equation you can write down, the solution you can write, this is a linear equation in terms of in this form where you have a Green's function which satisfies this equation. And you observe that this equation can be thought of as a Fokker-Planck equation of a biased random walker. So you can easily write down the solution. So in the scaling limit, the solution is this Gaussian. So we know the Green's function, we know this, so we know the full solution. So we put it in this and perform this integral. If you do that, you find that this kernel is given by this explicit expression where k0 is Bessel function, modified Bessel function of 0th order. So now we have explicitly all the terms. So we know these currents explicitly. We get these hydrodynamic equations, these non-local equations. Okay, but usually I am calling those equations as hydrodynamics, but usually the hydrodynamics equations are presented in continuous variables. So I need to take continuum limit. And remember that I started with the situation in which you have state that is evolving, is characterized by average fields which are slowly varying over space and also evolving slowly over time. So that means we can actually express that statement by considering this kind of temperature fields and the pressure fields, that these temperature fields are basically given by these functions of I and T, where you have epsilon and epsilon bar, which determines the scale. So epsilon inverse and epsilon bar inverse are macroscopic length and time scales measured in microscopic length and time units. So one convenient way to use this transformation, that I goes to X and T goes to S, like this. And if you do that, you will get, and then take epsilon going to zero limit and epsilon bar going to zero limit. Yes? Have a question? No. Then you get equations. So for the phasor field, you have observed that it actually has a convective part and a diffusion part. So it has a ballistic propagation. So this says that we consider this scaling form, and you get this equation. And if you choose diffusive scaling, you get a diffusion equation for the pressure field. But for the temperature field, if you do the same procedure, you get these terms where I have used this limit. So if you take this scaling limit of this kernel, in the scaling limit, it becomes this kernel in the continuous variables, X and Y variables. Okay, so I get this equation where you have epsilon and epsilon bar explicitly. Now, if you choose different space-time scaling, you get different equation. For example, if you choose ballistic space-time scaling, then you get this equation, and where you have epsilon and epsilon square root epsilon on both terms, which means that in this going to zero limit, you get zero. So that means the temperature profile doesn't evolve on the ballistic space-time scaling. But if you choose a super-diffusive space-time scaling, that is, remember, this was the variable associated with the time scale. So epsilon bar is epsilon to the 3 by 2. If you choose that, you get this equation. So this is a super-diffusion equation, super-diffusion equation, but you get a correction, diffusive correction with a small parameter. Okay, so I get this equation. So I should mention that this equation was derived by Cedric and collaborators in mathematics literature using a more different microscopic approach. Here I have given an alternative proof using a slightly different, approach. Okay. So what is the implication of this equation? So I can rewrite this equation in this form and identify a length scale, length scale which is epsilon c inverse, and in this form. And then I want to demonstrate that this equation exhibits a crossover in the following way. So imagine that you have an initial localized heat pulse at some position and observe its evolution, which is governed by this equation. So it will start spreading, but as long as this spread is much smaller than this length scale, this term will dominate, and that will be governed by a diffusion equation. So you'll have a diffusive spreading. But when the spreading is much larger than this length scale, it will cross over to super-diffusive spreading. And that's the crossover I wanted to talk about. But to demonstrate, it is better or convenient to demonstrate, or you can demonstrate clearly this crossover in this setup, which is this setup which Sattu was asking, with reservoirs at the two ends. So in this setup, of course, you have to add two other terms at the two ends. So the reservoirs are represented by Langevin reservoirs. So you have this term, Langevin reservoir, from this end, and this term from this end. And so your Fokker-Planck equation also get modified. You have an extra piece into the Fokker-Planck operator from the boundaries. And once again, I follow the same procedure, assuming a local equilibrium picture that is slowly evolving, and write down local equilibrium distribution plus a deviation, and write down this, and follow the same procedure. I'll get equivalently, I will get exactly same equation as and kernel in this form. Only difference is that the Green's functions are different, because now the problem of the corresponding random walker problem gets reduced to this problem, that you have a random walker which is drifted but with in a bounded domain with two absorbing walls at the two ends. So the walker is drifted this way, but you have two absorbing walls. And this is the Gin's function. And of course, to get the continuum limit, we have to consider this kind of scaling. So under this scaling, it turns out that even with this Gin's function, if you do this, you get exactly the same position representation of the kernel. The difference is that the boundary conditions of this kernel is different. So this is usually does not happen for a non-local operator. This happens for the Laplacian local operator, where the position space representation of the Laplacian, even in infinite line and bounded line, is exactly same, only the boundary conditions are different. But for non-local operators, it usually doesn't happen. But in this case, you have the same representation, only the boundary conditions are different. Okay. So just to make connection with the previous notation, so here epsilon is actually 1 over n. Okay, so for the temperature field, if you use this scaling form, you get this equation for the temperature field. This is, so you get a super-diffusion term and a diffusive correction, which is of order 1 over root n, and you have to solve this equation with these boundary conditions. So that's how the boundary conditions appear into this equation when you do it with reservoirs. Okay. So I would like to mention that this red part of the equation we had derived in another work with Priyanka, Oritra, and Ovishek from a completely microscopic approach, where we looked at the 2-point microscopic correlations of these eta variables and explicitly, and looked at the scaling properties. But that was a different approach. Okay, so in the steady state, of course, this time derivative goes to 0, and you get this equation for the steady state. So this is the temperature profile that you have to solve in the steady state with these boundary conditions to get the steady state temperature profile. And if you want to write down the current in the steady state in terms of this temperature profile, it looks like this. So this looks like the right-hand side depends on x, but it's not this equation. The solution of this equation ensures that the right-hand side is actually x-independent, because this left-hand side is actually x-independent. It should be a constant current in the steady state, non-equilibrium steady state. So since this is independent of x, so we integrate both sides from 0 to 1 over x, and you get this explicit expression for the current, as you have a 1 over square root n scaling in the leading order, and you have a diffusive correction. So this is the anomalous behavior. So the exponent is half, alpha is half in this case, and you have a diffusive correction. And once again, if you write down in this form, you can identify a crossover size, which is in this explicitly given by gamma and k naught. So in this form, you can easily see that when your system size is much smaller than the critical this crossover scale, you would observe diffusive scaling. And when your system size is much larger than this crossover scale, you would observe anomalous scaling. So that means as you increase your system size, you would go from diffusive scaling to anomalous scaling. So that's how. So in this non-equilibrium setup, it is more clear. You can demonstrate this crossover more clearly. So this is a numerical result that I wanted to present to demonstrate this crossover. So I choose parameters such that this crossover scale is much larger, so that you observe diffusive scaling, and that's what I observe, is 1 over n scaling. And then in this case, I choose parameters in such a way that the NC is very small, so that you don't even observe the diffusive scaling, you observe the anomalous scaling, where I see 1 over square root n scaling. But to see both of them, I have chosen parameters. You have to choose parameters such that this crossover scale is actually intermediate between these two. But so this is the best I could get. So below this, it is trying to reach this 1 over n behavior, but before it could reach there, it already crossed over to the anomalous regime. To see this from this exponent to that exponent, you need very large NC, And on top of that, you need to be able to, you should be able to find out these currents for ins much larger than NC also. That is very difficult to get numerically, but at least you can demonstrate in this way. Okay, so this is how I demonstrate the crossover. So this brings me to the end of my talk. So this is the conclusion. So I have mainly discussed anomalous transport in a 1D system with two conserved quantities, and I have considered the local equilibrium picture, and which local equilibrium picture that is slowly evolving and slowly varying. And from this, we find super-diffusive evolution for the local energy density along with the diffusive correction, and that kind of allows us to demonstrate a crossover from diffusive to anomalous transport. And we believe that our derivation is based on estimate, our derivation is actually based on estimating corrections from local equilibrium state, and I believe it is intuitive. And also, I believe that one should actually use this the non-local equation to study boundary wall problems. Here, I mainly discussed about problems in which you start with initial localized pulse and how does it evolve. But you can also think of problems in which you start with the configuration in which you have a boundary or like a step profile, and you ask how does it evolve. In such cases also, as long as the step size is small in general, but in this case, this is a harmonic problem, so I believe that if you take any size, it should work. But I believe one should use this non-local equation to study this problem also. So yeah, thank you very much.